All right, let's do some more buffer problems. So the first thing to recognize with this is that we have a buffer solution because we have a weak acid, we have acetic acid, which contains acetate, and we have sodium acetate, which is the conjugate base. So let's go ahead and list out our major things. We have a weak acid. We have sodium acetate, which will dissolve, and so we'll end up with a sodium ion and acetate ion. And then we have water. The water is pretty insignificant since the Ka value is so much higher, and sodium is not really going to do anything because the only thing it can bond to is the acetate, and that would form a soluble salt. So now we know that these two are going to be the determining factors for the pH. Let's set it up for the weak acid. So we're trying to see how much this is going to dissolve. And we're going to get a little bit of hydrogen from the water. We have our initial concentration of acetate because it's a 1-to-1 ratio with the sodium acetate. And we have an initial concentration of acetic acid. It's going to shift towards the 0. And now we can set up the K equation. We'll assume x is small. The 0.5s are going to cancel, and so now we know what x equals. And x equals the concentration of H+. That wasn't what the question asked for, though. The question asked what was the pH. pH is equal to the negative log of the concentration of H+. So now we can just take the negative log of that. Careful with your sig figs. We need 2 sig figs there. So that's one way you can solve this problem. However, remember we said this was a buffer. So there's a second way you can solve it. Because we know it's a buffer solution, we can just use the Henderson-Hasselbalch equation. So instead of setting up that whole ice box, you can just say that pH is equal to the pKa plus the log of the weak base over the weak acid. So we're going to take the negative log of the pKa, or sorry, the Ka, and we can set these two on top of each other. They're going to cancel out because they were both 0.5. So that's going to cancel out. Log of 1 is 0, and so now we can just take the negative log of 1.8 times 10 to the negative 5th, which will give you the same pH. So you have the choice now. You can, once you recognize that it's a buffer, you can either plug everything into that equation or you can set up an ice problem. All right, let's look at another one. This time says, calculate the pH of a solution where we have some lactic acid and sodium lactate. So again, we have a buffer solution. So you do have another choice. You can set up an ice problem, or you can just recognize that you can use the Henderson-Hasselbalch. I'm going to use the Henderson-Hasselbalch because I think it saves a lot of time. So pKa plus the log of the concentration of lactate over the concentration of lactic acid. Make sure you put the acid on the bottom. Take the negative log to get the P version of it. And the lactate was 0.25. Lactic acid is 0.75. Plug all that in and you get your answer. All right, this is our last buffer problem for today. This one's a little bit more complicated, so stay with me. This time we are going to, let's just start by listing our major species. So we have several things going on here. We have sodium hydroxide, we have some HF, and we have some KF, all kinds of stuff in the solution. Sodium hydroxide is a strong base, which means it's going to dissociate 100%, close enough to 100% that we just rounded to 100. So instead of having sodium hydroxide, we actually have sodium ions and hydroxide ions. We also have some weak acid, and we do not break apart weak things because they mostly stick together. And we have KF, which is a soluble salt. K is group 1, and soluble salts, or group 1 always makes soluble salts. So we actually have K plus and F minus. We also always have some water. So now it's time to figure out what is going to actually react. Let's start with the sodium. Well, there are two things the sodium could stick to, hydroxide or fluorine. Either one of those two are going to immediately break apart because it's either a strong base or a soluble salt. So the sodium has nothing that it can do. Same thing for the K plus. It can bond to hydroxide or fluorine, but they would immediately break apart. The water is pretty insignificant because the Ka value for HF is much higher. And now we have three things that we need to figure out what to do with. Once you list your major species and you've crossed off things that are not going to do anything, what I want you to do is to watch for H plus or OH minus. And if you have either one of those two, you need to start with that ion, either H plus or OH minus, and you need to react it to completion. This is a strong base, and so it is going to react with anything it can react with until it cannot react anymore. So let's start with hydroxide, and let's see what it can react with. It's not going to react with the fluorine because that's negative, and two negatives don't like each other, but it can definitely react with HF because that's a weak acid. And so it's going to strip the HF of the hydrogen and create water and F minus. So now we have our first reaction. This is not an icebox because the purpose of an ice problem is to figure out how much something dissociates, and we do that for weak acids and weak bases because we don't know how much they dissociate. This one, we know hydroxide is going to react to completion. So it's going to be set up similar to an ice problem, but we're going to call it a before, change, and after. We're not talking about equilibrium here. We're not trying to see how much it breaks apart. What we're trying to do is just see how much will be left after all of the hydroxide reacts. So this is a BCA problem. So let's go ahead and put in what we have initially. We've had an initial amount of this one. We have an initial amount of fluorine. And we do need to calculate the moles of this. And that's our initial amounts. And then what you're going to do, so this ends up being 0.1 molar. You're going to react it to completion. So again, this is not adding X. This is not equilibrium. It's completely different. It just looks kind of like the nice problem. We're going to react it to completion, which means we're going to use up whichever one we have less of. So in this case, we have less hydroxide, so we're going to run out of that first. So we're going to use that up completely. And that means we're going to also use it up here. And we're going to add it over here. Water's a liquid, so we're not including that. So now this comes down to 0. And when you have hydroxide or hydrogen ions, they're going to react until either they are 0 or the thing you're reacting at goes to 0, whichever one you have less of. You're going to subtract it out until you have 0 of one of them. So now this one, after it reacts, becomes 0.5 molar, and this one becomes 1.1 molar. And now at this step, notice that we have some HF. We don't have any more hydroxide. It reacted to completion. And we have F minus, and now this is a buffer solution. So at this point, you have a choice. You can set up a new icebox to see how much the HF is breaking apart. So you have H plus, you have F minus, you plug this in here, plug this in here, and then do your normal ice table. And you can figure out the concentration of H plus, and then you can take the negative log to get the pH. However, because it's a buffer, you can also do the Henderson-Hasselbalch equation, which is what I'm going to do. So now we have pH is equal to the negative log of the Ka, which was 7.2 times 10 to the negative 4th, plus the log of the weak base, in this case is 1.1, over the weak acid. and you just plug it all into your calculator. And if you had done the ICE table, you would end up with the same thing. So you would just plug in those amounts, you would do your minus x plus x. X is going to end up being the concentration of H plus, and then you can take the negative log and you'll still get 3.48. And those were the examples for today.